So we'll talk about transistors. So all we're going to do is add another PN junction. So today we have essentially two types. There's a lot of variations within those two. Um, we have what we call bipolar, which are junction type devices, where we have either PNP or NPN material. And then we have field effect devices, which also use the P and N material, but they use an electric field or electrostatic field to control the current flow as opposed to current in the bipolar devices. So we have to apply a control current in the bipolar device to control the amount of current flow between the base and collector. In the case of field effect, we apply a voltage to the gate to control the current flow from drain to source or source to drain, whichever way you go, because they're symmetrical and you can actually reverse it. It doesn't care. Typical symbols you'll see, the standard junction bipolar transistor is a three-terminal device with an emitter, a base, and a collector. And this bar is kind of representing I guess, the substrate. And you've got the base material with this connection, the collector material here, and the emitter there. And it has a little arrow showing the current flow, not electron flow. Old Benjamin Franklin again. And that's for an NPN. If it's a PNP, symbol's the same except we reverse the arrow because the current flows in the opposite direction. In the case of a field effect, we have junction field effects and we have metallic oxide semiconductor field effects. So they're represented differently. The junction one looks very similar to the junction transistor, except they kind of square it off to show the channel. And we have a P type and an N type, just like we do in the others. And you see the little arrow showing essentially current flow, although it's potential in this case, voltage, because you have very minuscule current. In theory, you have zero. It works like a vacuum tube. And then the NMOS versions or MOS version, both P and N, and you can have enhancement and depletion modes, and it gets really complicated. It's a much more complicated looking diagram, but they do have the little arrow again showing conventional current flow or potential. So what is a bipolar junction transistor? It's this sandwich that allows a small current injected into one of the terminals, usually called the base, to control current flow between the collector and emitter. And that allows us to use it as a switch or an amplifier, depending on how we bias it. We can have it biased such that it's off and we turn it completely on into saturation. Or we can bias it in the middle where it's on all the time and we vary the amount of current that flows. It would be like a type A, class A amplifier. You got to remember the three terminals, base, emitter, collector. A little diagram here of kind of a typical cross section, the way they make them. I've never actually seen the process, but they always show it as these embedded layers where the base material is separating the collector and emitter material. And in this case, it's an NPN. If it was a PNP, we just change the letters around. In most cases, the collector material is going to be much larger and much more surface area. And of course, once again, you've got, your barrier potential at the junctions. The one you care about is the base emitter junction. It's going to be same as a diode, whether it's germanium or it's silicon. It's going to be the 0.7 or 0.3. And you're going to have a depletion zone, just like you do in a diode. Yes.
Um, the amount of current that flows through either an NPN or PNP transistor would be the same current going, essentially the same current going through the emitter as going through the collector, right?
No,
No?
no.
Oh,
Collector current will be less than the emitter current. Remember, the emitter current is the collector current plus the base current.
so why are most transistors, why is the heat sink on the collector instead of on the emitter?
I don't know.
You're an extra, you're supposed to know.
That's not a question. You should submit it. Um, that's a good question, but I don't know. I assume because it has the most material that it's going to dissipate. I mean, the whole thing is going to get hot at the junction, and it's the junction where that you're really trying to cool.
Between the N and the P and the,
Well, actually, guess both of them.
yeah,
But yeah,
both sides of that P.
I guess it's the best way to get the heat out, would be my guess, just mechanically.
Well, you've got, I mean, the contact area is what's going to dissipate the heat.
Right. And the collector has much larger surface,
Yeah.
Right. So the larger
which is
surface
maybe why they make it bigger to
is
get the heat out.
Yeah.
Well, if there's less current going through,
Well, not much.
well, I know, it's the difference is the base current.
Right.
Which is usually pretty small.
Right.
But if, so they, for the argument, let's say they're the same, forget the base current.
Okay.
Because it is really small. So I guess they just chose, why do they use so much more material, or is that just the diagram? It looks like there's a lot more of the collector material than the emitter material.
Well, the way I understand the process, and it may be totally off, but they start with a silicon wafer. Okay. And somehow they manage to dope it by getting these impurities to create an N or P region into that wafer. They use some kind of stereolith mask and gas it or something and infuse. I've never actually seen the process, but they actually make all these little transistors on that one big wafer by embedding it in that silicon. So the cross section looks something like that. So you're going to have a intrinsic silicon wafer regardless material, and you just embed this stuff in there. And then you chop it up in little pieces to make transistors. I was just part of the manufacturing process, I assume.
That's the largest part of the transistor, so they would use that as the heat sink, I guess.
Yeah. Because these things are really small.
Small.
Okay, so we represent, like I said, the bipolar as an NPN or PNP with the little arrow in or out. Kind of how it works is when you apply a potential to the base, it can create a current between the base and the emitter. Okay. It has to cross that barrier. So that's why we got the 0.7 volts or the 0.3 volts. And somehow current going through there has an effect on the electrons, and it sort of causes some sort of avalanche effect where you get electrons traveling from this highly doped region over to the collector. And that's your emitter collector or conventional collector to emitter current, but it's electrons going the other way. As a result, and it's a multiplication factor, which we call beta or HFE, which says for every microamp of current base emitter, you're going to get so many milliamps or whatever of current collector to emitter. That's the amplification factor. Turns out the smaller this base layer is, the higher the beta can be. Now, obviously, when it gets down so thin, you can have voltage arc over. So there's a minimum how thin it can be. So far, that's why high amplification devices like operational amplifiers, things like that, can have a very thin gate region in the transistors, but they also operate at low voltages and low power. Okay, so when you forward bias it, like the diode, you get a little current to flow, which magically causes a large current to flow. We call that the current gain or the beta. You see it as HFE. If you got a multimeter that's got 3 little holes, you can plug a transistor in and measure the HFE. That's just the ratio of collector to base current. A typical circuit where we're applying a base current, we're getting current flow through that load resistor. So we draw a load line, which is the point from maximum current with all the way down to minimum current, maximum voltage. So when it's off, whatever this voltage is what you're going to see on the collector. When it's totally on, you're going to see almost zero, but then you got some barrier junctions there, so it won't get to zero when it's in saturation. They usually draw these separate lines showing different values of base current. If you look at in a data sheet for a transistor, and you'll see a bunch of these to make it easier to figure out what the base current would be where it crosses this what we call the load line. And the slope of this line is the value of this resistor, the load resistor, or a tank circuit impedance. So if you're going to do it as an amplifier, say it's a Class A amplifier, you would bias it about the middle so that it can operate in between these two extremes. If you're doing it as a switch, you're going to bias it such that it's at cutoff or below, and then you can turn it on all the way to saturation. So you may apply a little more above for saturation and a little less for cutoff. So what are the operating points for a bipolar transistor used as a switch? Which of the following indicates that a silicon NPN junction transistor is biased on? Remember, resistance is not a factor. At least not in this question.
Yeah, go. Yeah.
0.6 to 0.7 volts if it's silicon. and it said silicon. What's the beta of a bipolar junction transistor? Remember, it's a ratio.
It's not that hard necessarily. That's so bad.
Whoop. Okay. This is an unusual one, but it's on the exam. The alpha cutoff frequency. When I was researching, I had a hard time finding this. It's not very, it doesn't show up on most data sheets. I don't know why we care, but it's defined as basically the 3D, the half power point or 3 dB point when you have a grounded base configuration of the 3 dB down point relative to the gain at 1 kilohertz in that amplifier. So if you set up that configuration and you vary the frequency, when you get down to 3 dB less gain than you had at 1 kilohertz, that's called the alpha cutoff. Is that clear?
You grounded the base, though, it's gonna be.
Huh? Well, in a grounded base, it's a voltage amplifier. There's no current. Actually, current is less.
Yeah.
So it's not quite a one-to-one current amplifier, but it's a voltage, high voltage. I mean, yeah, high amplification for voltage.
Base is not grounded.
Well, they consider it grounded because it's going through that resistor. That's just giving a little bias. It's just like a grounded grid transmitter tube. That grid is not always connected directly to ground. It usually goes through a little parasitic LC and or resistor.
So what's this going here?
It's a one-to-one current amplifier, but it's also a voltage amplifier. And what you're doing is finding out at what frequency does the gain drop 3 dB below what it was at 1 kilohertz. They just use 1 kilohertz as a reference. So whatever the gain was at 1 kilohertz, when it gets down, it gets to a frequency where the gain is 0.707 of that, they call that the alpha cutoff frequency. Because higher frequencies is just going to keep going down and down. So that's its usable range in that configuration. So I don't know why most people care, because like I said, I couldn't find it on data sheets. Took a lot of research to find that.
Just memorize the answer.
So what is the term for the frequency at which the grounded base current gain of a bipolar junction transistor has decreased to 0.7 of the gain obtainable at 1 kilohertz? You'll remember that one now, right?
I won't remember why.
You don't need to know why in this case. Okay, so we talked about junction transistors, current devices, current control devices. So we're talking about field effect transistors, which work more like vacuum tubes, where it's a voltage control device. In other words, the voltage control the current flow. Because they're all current controlling devices. So we make use of an electric field to control that current flow, and a lot of times they call it a channel between the source and drain. And it can be a P channel or an N channel, just like in the other. You have kind of both sexes. It still has 3 terminals, typically, called source, gate, and drain. I think there's some that have a fourth where they have multiple gates. Not really familiar with those, and that's not part of this. But the basic thing is they control the current by the application of voltage on the gate, which is producing an electrostatic field. Then we have it broken into two kinds, a junction type or a metallic oxide type, where you still have some junctions, but the gate has an insulating layer of a metallic oxide between it and the rest, which is where the metallic oxide, the MOS part comes in. It still uses an electric field to control the channel. A field effect transistor, let's see, 3 terminals, we talked about that, can be P and N type. Here we have 6 different ones, where one is a P-channel junction FET. 2 and 3 are P and N-channel MOSFETs. 4 is an N-channel dual gate. Now there's another 4-terminal one. And then we have a P-channel dual gate, just the opposite configuration of P and N's, and an N-channel junction FET. So in figure 6.1, what's the symbol for an N-channel dual gate MOSFET? I mean, it pretty much has to be 4 or 5, right? So if it's an N-channel, which way does the little arrow go?
Yeah.
Well, let's see. How about that? What's the symbol for a P-channel junction FET? Alpha. Okay, a MOSFET, we separate the gate with this oxide layer, but you still have a field between the gate and the body of it. And that kind of bluish part is called the channel. So that's what you're using the electric field to restrict flow through that channel or enhance flow, depending on whether it's a depletion or enhancement mode device, which we'll get to in another slide or so. So you can have current flow from the drain to source or source to drain. And if you notice, it is symmetrical, so it really wouldn't care which way you hook it up. Not the case with a bipolar transistor. So which of the following describes MOSFET construction? What's MOS stand for? Yeah. Metallic oxides are typically insulators. And that's what the purpose of it here is, to insulate, so there's no junction between the gate and the body of it. So it just lets you create an electrostatic field without having that gate junction.
The body's providing the extra electrons needed to make the.
Yeah, what's the body doing there?
It's this.
It's just conducting current from the drain and source. Current flows from drain to source or source to drain, depending on your flavor, through the P material.
So the P material has holes. The body's providing those extra electrons, which are.
Right.
going into
So every time you fill in a hole, okay,
the-
you create another hole and you get your quote current flow.
What's the gate? How's the gate affecting that?
Well, the gate is creating an electrostatic field across this. Okay, and that between that gate and this body,
Oh,
and that field is going to in some cases they talk about a pinch effect. Okay, it pinches the size of the gate down. I don't know how, when you get down into the atomic terms, how that works, but it can restrict the flow the higher the field. Or just the opposite, because as I mentioned, there's a enhancement mode and a depletion mode. And in one case, I don't know that I can ever keep them straight. Enhancement mode, a positive voltage enhances the flow. In depletion mode, I think it's a negative voltage decreases the flow. So in depletion mode, with zero voltage or potential on the gate, you have maximum current flow. And by applying a negative voltage, just like a vacuum tube, you start restricting the flow. In the case of the, and I'm getting ahead on the charts, case of the enhancement mode, you have, with zero bias, you have zero current flow. And as you apply a positive field, it enhances or increases the current flow. We'll get another chart that shows that.
I'm gonna write down this
Okay.
reference here so I can look it up.
Okay. Okay, so one thing MOSFET transistors have is a very high input impedance. And I think it's partly due to that insulating layer. Okay. So a bipolar transistor is very low because it's a current input. So it's very low in input impedance. You kind of see these in test equipment, like front ends on voltmeters, things like that, because you want a very high input impedance. You don't want to load the circuit. You see on a oscilloscope amplifier, vertical amplifiers, things like that. Because of that, they're very sensitive to electrostatic discharge because of that high, because they can be megohms. So they actually, in a lot of devices, will create Zener diodes on the gates and sometimes on the drain and source to prevent ESD. If they don't have it or enough, a lot of times people will put Zeners externally to do that. Here's one that's got a lot of it built in. You see there's back-to-back Zeners, so it can protect the voltage in either polarity, and one across the source and drain. So that you can't, in this case, you wouldn't be able to use it, switch it around between source and drain. If that Zener wasn't there, you could. So how does DC input impedance at the gate of a field effect transistor, or FET, compare with that of a bipolar transistor? High input impedance.
I remember when these things were first introduced, the big thing was that they more closely resembled a vacuum tube.
Right. Right.
And that's how people started accepting.
Yeah. What's the purpose of connecting Zener diodes between a MOSFET gate and its source or drain? Bravo or Delta?
Oh, there you go, down here.
Read them all. Yeah, on the exam, read all four answers before you pick one. A lot of times you'll see one and you just think that's right.
It's not horrible, problem. It's sort of.
Okay, so I talked about enhancement and depletion mode versions. Most of them are enhancement mode, okay? So you have to apply a voltage to get current to flow. So they normally are off. And you have to bias it to generate current. The depletion mode is on, and you have to turn it off, where it's more like a vacuum tube, because the vacuum tube without a gate control voltage is going to conduct. And this is kind of showing kind of the cross section between the two types, and where you have a P channel inserted between the source and drain, as opposed to the normal N channel, which makes one depletion mode as opposed to enhancement mode. And I think that's all you have to remember in this case. But,
Is there a
they
difference
still have.
Is there a
Go
difference
ahead.
between the voltage applied for the to the gate in enhancement versus depletion mode? In other words, is one positive, the other negative for the gate voltage,
Correct.
or are they both positive?
No, one's positive, one's negative.
They differ by the activation voltage.
I
Usually,
didn't hear that.
they usually differ by the activation voltage.
Right. In one case, you got to turn it on. And in one case, you're going to turn it off. So the negative bias turns it off. That's acting more like a vacuum tube, a triode vacuum tube, where a positive voltage is going to turn the enhancement one on. So what is a depletion mode field effect transistor?
A,
I believe it's alpha.
Well, let's see.
Broke your rule.
Oh, you got to do that. If you don't, you'll miss them, because they try to trick you. They'll put one in there that sounds pretty good. So now we know everything we need to know about